I'd like to introduce our speaker today. Our speaker today is originally from Toronto. He's been for the past couple of years, he's been teaching at the Massachusetts Institute of Technology, where his students included a couple of people you might know, people like Jim Flanagan and Arthur House and Victor Zhu and Jack Godfrey, I believe. Is that right? No? Okay, sorry.
With Mark Johnson.
Yeah, and he's going to talk to us today about ways in which the speech science and technology can benefit the study of linguistics and vice versa, and in particular about a few theories that have been developed in collaboration with Jay Kaiser and Morris Halley and other people like we described. Thank you, Ken Stevens.
So, this is a list of the people, some of the people I've collaborated with, and there are some other graduate students as well. So, what I'm going to try to do, let's see, is talk a little bit about a model that sort of drives our own research. And in the course of doing this, I'll give a little bit of background on what we think of as distinctive features, and then talk about where those distinctive features come from, what their acoustic correlates are, and then discuss some of the sources of variability in the acoustic manifestation of these features, both something we call enhancement and something that people have called gestural overlap. And then finally a little bit about how this model might be revised. So this is sort of a standard model for sort of human lexical access, where you have an acoustic signal and you want to get some words out of it, and you have a lexicon, and you have to do certain things with the acoustics in order to get there. And in our case, we assume that the lexicon is represented as bundles of these distinctive features that the linguists have talked about. And then later on, I'll talk about an extension of this, which is of the kind that many of you, I'm sure, have seen before, where you have some sort of feedback or top-down processing as well as the bottom-up processing. And I'll come back to this later on. So we have some proposed words, and we want to resolve which among these words gives you the best fit. So let's first talk about this distinctive feature stuff. And before I get too far into it, I just want to say that this term feature that we've taken from the linguists is kind of different from the term feature that many people who do pattern recognition use. For these linguists, and for me, I guess, these distinctive features are binary to start with, so they are present or absent, if you like, or plus or minus. And they're kind of abstract. That is, they're ways of representing how words might be stored in memory, one of the ways in which those words are stored in memory. There are a lot of other ways in which these words are stored as well. But the main thing about a feature is that changing a feature value from plus to minus or minus to plus has the potential of changing to a new word. That's sort of the way you might define a feature. So you can change the initial consonant, the voicing in the initial consonant, or you could change the place of articulation of that consonant from P to K, or change a feature of the vowel. Okay. So, and so that words then are represented in memory in this sort of what might appear to be a kind of complicated way. Each one of these columns is one of these things we call a bundle of features. These are lexical, sort of proposed lexical representations for a couple of words, the word sudden and the word help. And these features are divided into two groups. I'm going to for the moment, leave out this reducible and stressed. I'll discuss maybe those later. But the upper group of features we call articulator-free features. The lower ones, articulator-bound features. The articulator-free features are sometimes called manner features. They are things like it's a vowel, or it's a glide, or a consonant. Or if it's a consonant, it's a continuant, or a sonorant, or a strident. And then and as we'll point out, those particular features are responsible for creating landmarks, special kinds of landmarks in the signal. And then in the vicinity of those landmarks, quite often there are cues or information about the articulator-bound features, which are expressed in terms of articulators or what you do with those articulators. I guess another thing to point out is that this representation in terms of features is kind of sparse. That is, we don't have to specify a plus or minus in every entry. And part of that is because if you are given one feature, then that automatically means that another feature is not relevant. And I have to say, the way we're setting up these features, they're not, strictly speaking, all of them binary. Some of them you might call unary. So if there's a feature that says you use the tongue blade, then it automatically means you're not using the tongue body or the lips, at least in English. Okay. So that if one wants to sort of access from the acoustics words of this kind, the number of features that you have to determine is not that large, right? Once you've got the manner features, the articulator-free features, on the average, only somewhere in the range 3 to 4 features is what you need to determine. Okay. Okay, so this is a suggestion of the way, in terms of, at least based on various kinds of evidence, the way these words are stored in memory. So these are a couple of spectrograms, and I'll be showing a few more, which illustrate some simple aspects of the acoustic correlates of some of these features. So you see these sharp discontinuities in the signal. There, and there's one here, and maybe one over here. And those are these, you might call them abrupt kinds of landmarks. They are places in the that show up in the signal when you make a constriction, when you make a consonant, basically. You make a narrow constriction, and the consequence of that narrow constriction is either to shift the source of excitation of the vocal tract, or to make some sudden shift, let's say from, in this case of a mat, a sudden shift from, let's say, taking an output from the nose to switching the output to the mouth primarily. Okay. And so in both cases, you get these abruptnesses. And then the other kinds of landmarks are not so abrupt. For each vowel, you have some kind of peak in energy, particularly in low frequency energy. Here's a vowel, another vowel here, and over here. And the other kind of landmark, you might call it a glide landmark, where you have a minimum in energy, but again, no abrupt discontinuity. So those are the landmarks, and those are in the model that we have in mind, if you can find those landmarks, then you look in the vicinity of those landmarks to give you some additional information about the articulator-bound features. Okay. So for example, over here, there's a landmark, and then if you look on both sides of this landmark, you will be able to get some information about the fact that this is a nasal, and there's some acoustic information that will tell you that, both in the vowel and in the consonant and in the discontinuity. And If you look in the if you look at how the formants are moving or how the spectrum is changing, that will tell you something about the place of articulation of the consonant. And if you look in the middle of the vowel, if you can find the formants, you would be able to get some idea of the features of the vowel. In this case, it's a vowel a, so it's a front vowel, and it's a what we call a low vowel. Okay. In the case of this glide, you have this minimum, and the way the spectrum is changing in the vicinity of that minimum will tell you that it's the w and not a y, which are the two possible glides. Then you have other features, like this is a plus continuant. It's a fricative because it has continuous noise. Here we have an interval of silence, and of course it's a stop consonant. Okay. Now, I'd like to, these features were first discussed way back probably in the 1940s or 1930s, okay? And they've undergone certain changes, and they were first conceived of by linguists, and it was in about 1952 that Gunnar Font, an engineer, came into the picture trying to sort of explain what the acoustic correlates of these features are. Since that time, there have been some changes in the features, partly as a result of work of the linguists Chomsky and Halley, and more recently, some work that we've done on trying to give some sort of acoustic and perceptual and articulatory justification for these features. So in doing that, we examine the relations between parameters that describe the articulation and parameters that describe the acoustic and perceptual consequences. So we're studying, if you move the articulators around, what's the relation between the articulator movements and the acoustics that comes out. Okay, so this is a picture I've shown many times before. So if you have, quite often what happens is if you manipulate some articulatory parameter, let's say the degree of opening of the mouth when you're making a stop or fricative consonant, for example, and you look at the acoustic consequence of making this change in articulation. And quite often you get not a sort of smooth monotonic relation, but a relation where looking at how the acoustics changes with articulation, the change is very small over this region 1 and small over region 2. And then there's an intermediate region which is less stable. Small changes in articulation will give a larger change in the acoustic parameters. And what we tried to argue is that the preferred regions for generating sounds in language are these 1 and 3, and then occasionally you have to cross this boundary. So I'm going to give just a few examples of well, this just describes what I just said here. And these examples will be drawn from this list. That is, we've looked at a number of these features and tried to see to what extent there might be this kind of quantal relation. And some of them we haven't been worked out completely, the ones with a question mark, and others. But let's look at just 2 or 3 examples. So, for example, if you look at a fricative consonant, or look at one of these, what we call obstruent consonants, where you're made with a narrow constriction in the vocal tract. And if you change the size of this constriction, let's examine how the amplitude of the turbulence noise changes as you do that. So here we're plotting along the x-axis the area of the constriction. but not the actual area. Since when you make these consonants, you're going to build up pressure in the mouth, and that pressure in the mouth is going to exert a force on the articulator and is going to push it open a little bit. And so that even when the resting area of the constriction is 0, the actual area might be some finite value. Okay. As if you make a sort of a T very lightly without building up the pressure and then build up the pressure, it becomes a fricative because you've pushed the mouth open. Anyway, if you make this area small enough, you'll get no noise, right? Because you cut it off completely and you get no noise. And if you make the area large enough, and given that you have a certain size of constriction at the glottis, if you make the area large enough, again, it will not generate any noise. All the noise will be generated down at the vocal folds, at the glottis. Right? So it stands to reason there's going to be some peak in here, which would be an optimum place in which to set the cross-sectional area, the resting cross-sectional area of the constriction. Okay, so this is kind of a stable region, not so stable out there. Okay. So that's just one example.
Just a clarification.
Sure.
In the previous plot, you had concrete numbers at the bottom rather than just a cartoon. So I
Yes.
think this was actually measured.
I'm sorry, I should have said that this is a model. This is a calculation, okay, knowing how noise gets generated and how it's dependent on flow and so on. So this is a model, that particular one. Now, one of the features that's pretty universal, is universal, is feature back. So we distinguish vowels as to whether they're front or back, E versus U, or let's say E versus A versus A, and so on. They're distinguished by a feature called back. And so it turns out that if you, might be easier to look at this one over here. These are actual data. If you look at a diphthong like I, at least for some people, and if you look carefully for most people, and if you look at some measure of how the formant is changing as you go from A to E, you often find some kind of discontinuity at some point along the line. This is the second formant. And it seems that that happens based on some additional data that some of my students have, that this happens at a time when the formant, that is the natural frequency of the vocal tract, passes through the natural frequency of the subglottal system, right? So you've got, and it's for the subglottal system, it's somewhere around, depending on the speaker, can be anywhere from 1500 to 1800 hertz, okay? So you know that from sort of theory of coupled resonators, if you have two resonators that are very close together, they'll push each other apart, and you'll get a discontinuity. And it's not possible to create a situation where there's a major peak at the halfway point, where both of these resonances are equal. So in fact, this is kind of an unstable region, and so that what seems to happen if one looks at languages across the world, by and large, is that the front vowels are above that line and the back vowels are below. So there's a line drawn schematically here at about 1500 hertz, that all the back vowels are down here, plotting F2 versus F1, front vowels are up there, okay? It's a little less clear, and we still need to work on that a little bit. It shows up in this particular case that there's also a discontinuity down here, because it turns out that the first resonance of the vocal tract of the subglottal system is around 600 hertz, and this one is the second resonance. So sometimes you see a discontinuity, but that one is not so clear, and still need to figure out what's going on there. So this just is a schematic way of showing that if you plot the frequency of well, the frequency F2 with a closed glottis, and if you change that frequency, you change it along this straight line. But if you would assume that there's some subglottal resonance, then the actual frequency you will see will take a bit of a jump at some frequency around 1.5 kilohertz. So that's another example of feature. Let's see. One other example is feature anterior. So when we make an S, we make a constriction at somewhere near the front of the vocal tract. And we can make other fricatives or stop consonants by moving the tongue blade to different positions. The acoustic property of a fricative or a stop that's made at this place with this configuration, it usually generates some kind of noise as air, we build up pressure back here, we generate some kind of noise, and that noise is probably most prominent at this obstacle of the lower teeth. And anyway, that noise excites the high frequency resonance in this front cavity. So you can think of this whole vocal tract as having a set of natural frequencies. And most of those natural frequencies are associated with the back cavity, but at least one of the higher frequency natural frequencies is associated with the front cavity. In this particular example, it's probably about the 5th formant that is associated with the front cavity, which means that the noise excitation is primarily of the front cavity, and so you mostly will get a peak in the spectrum around the 5th formant, let's say 4 or 5 kilohertz. And not so much excitation of the back cavity given this kind of source. Okay. Now if you move this constriction back a little bit, the back cavity shortens, the front cavity lengthens, and you may shift from a situation where this is the 5th resonance to the one where it's the 4th or perhaps the 3rd resonance. So you get, due to coupling of these, and that shift will be a fairly abrupt shift. So you'll go from an S to a sh, let's say it's sh, and you get some kind of abrupt change. And if you just sort of plot as a function, this is again a model, as a function of the front cavity resonance, you get regions where the front cavity resonance will, or prominence in the spectrum will take these jumps as you make it longer. And we recognize that when the front cavity is in this frequency range, that corresponds roughly to a sh sound. And when it's in the F4 or F5 region, where the auditory discrimination is not so good, it corresponds to an S sound. Okay. So there seems to be some kind of natural boundary there. Well, this is just a comment that the voicing feature also, and I won't go into that in detail, is also kind of quantal. I mean, it really comes from the fact that the vocal folds will vibrate only if the sound pressure across the vocal folds exceeds a certain threshold. Okay, it's kind of an oscillator that needs that threshold to operate, and that the threshold depends upon the stiffness of the vocal folds, and there are models that will show that. So that's another example of this kind of, you might call a quantal relation. So that these examples and others sort of, since they're sort of showing a kind of something about the relation between the acoustics and the articulation, that they can be considered to be defined, if you like, in terms of an articulatory action and the acoustic property it gives rise to. Okay, so for each of these, there's an articulation and acoustics that kind of go together. It's sort of a property And given that the acoustics is perceptually salient, which is another question, then it's sort of a property of this system. Okay, it has these quantal kind of regions. So linguists tell us that, at least many of them do, that in the languages of the world, there's sort of a universal set of these distinctive features, which are properties of this system, and that any given language, like English, will pick a subset of these properties in order to make their distinctions between words. Okay, and it would be speech recognition would be very simple if that's what happened, right? You always get this acoustics when you make this sound. Okay, but that's not the case, as you know. These defining, so if we call these defining articulations and acoustic properties, they only give a partial specification of how the feature is to be implemented by a speaker, and for that matter, how a listener can uncover the feature from the sound. So I'd like to now turn to some discussion of why that is and what are the sources of variability that makes it not that simple. Okay. And one of those is something that some people, including us, have called it enhancement, that you need additional gestures to enhance the perceptual saliency of a feature over and above these defining gestures, okay, by strengthening a defining attribute or by adding a new property. Okay, so we call those enhancements. So, and we can give a lot of examples, and I will talk about some of those examples. So, for example, well, let's go to one. Well, before I do that, so just to give an example, I talked about this sh sound, which is where you have this F3 as the major resonance that's being excited. And that depended on moving the tongue blade around. But in English, we know that I think most of us round the lips to make it sh, right? We do it that way. And that will actually make sure that that front cavity resonance is in fact in the right region. But at least we don't usually think of that sound as being plus rounded, because it doesn't make a distinction between other sounds. So it's an enhancing gesture. That's a simple one, but this is a list of some of the enhancing gestures that we've been looking at, and other people have too. Rounding of the lips for sh, but not in Mandarin. And in Mandarin, it's not really a sh, but in Mandarin you don't, at least in Mandarin, Chinese Mandarin that we know, it's not, the lips are not rounded, but something else is being done with the tongue blade to create a space under the tongue blade. And so the enhancing is done a little differently in Mandarin. In English, if we think of, and there are some reasons for this, if we think of the basic feature for voicing to be whether it's stiff vocal folds or not, then there are some contexts in English where we aspirate those stops, namely in the pretonic position. So we say pa, but we say top, and we don't necessarily aspirate the P in the word top or in the second P in the word paper. So we think of aspiration as being an enhancing gesture. That is, in English, a voiceless stop might be aspirated, but it's not the feature plus aspirated. Okay. There's some thought that when you make a nasal vowel, particularly in French, that you enhance the low frequencies, and that there's a little bit of evidence that you do that in part by spreading the glottis, which will help to enhance the low frequencies. Yes? Mm-hmm.
Is there evidence that this happens, for example, if people are in noisy conditions, if you're talking over a lot of noise?
these
Are
things,
they exaggerated?
they might be, yes, but these enhancements that I'm talking about are probably happen most of the time, and they may be enhanced in noisy conditions. I don't know of evidence for that.
Aspiration reminded me often when I'm talking to someone on the phone.
Yeah.
I tend to say P without any aspiration.
Yes.
They get it wrong, they make it B.
Yes.
Then I have to say P.
Yes, right, yeah. Right. But that's because of your background a little bit, of course. Yeah, okay.
So
Yeah.
I'm not doing the regular thing.
Right. And let's see. Yeah, so another one is tongue-body fronting for alveolars in English. So in English, I was pointing out that for, let's say, for stop consonants, that the properties of the burst, that is the defining property, but there are some properties of adjusting the tongue body, which I'll talk about in a minute, which we think of as enhancing properties, and so on. So let's just look at some of these. This is spectrograms of the word sip, ship, and then some effort to what would happen if we made the sh, which was not rounded. Okay, so this is a regular ship, and this is the spectrum, which shows a nice peak here in the third format region. The S has a much higher peak. If you don't round, you still get some kind of a peak here, but it's not as strong as this one. So it's sort of kind of an example that was manufactured, if you like, to show if you don't round the sh, you will not get such a strong distinction with the S, particularly if you think of the auditory system as compressing the high frequencies. Okay. Or if you look at, you're very familiar with this, if you look at the same vowel but preceded by an alveolar consonant, by a labial, and by a velar consonant, that the position of the tongue body to produce these tongue body as opposed to the, let's say, the position of the constriction over here, the position of the tongue body is pretty much defined by how you make this G. And for B, the position of the tongue body is not specified. It just takes on values that are close to the values for the following consonant, following vowel. But you do have some ability to manipulate the tongue blade when you're making an alveolar, the tongue body, when you're making an alveolar consonant. And what seems to happen is that the transition from the, for the D here is adjusted so that it's sufficiently distinct from this transition or from this one, which is not as high as that one. So the higher F2 means that you fronted the tongue body, which you don't necessarily do in all languages. And that we think of as an enhancing gesture. Okay, that is, you don't call these alveolar consonants minus back, because that's not distinctive in the language, but it's an enhancing of this feature of which we call plus anterior. Okay. Yeah, this is the one in this is in French, where you have the word combat, and the first vowel is nasalized, and just showing that when you make the nasalized vowel, you get a big enhancement of the low frequencies. It's considered to be in part possibly because of a sinus resonance, but it seems as though there's also some spreading of the glottis, which will enhance that distinction between the non-nasal one and the nasal one. This is the second vowel in combat. So again, spreading of the glottis is not considered to be an enhancing, a distinctive feature for French. It's nasal is the feature. Okay, so that's one. So these enhancing gestures then have to be taken into account when you're trying to figure out what cues to use to identify these various features. And so this is the use of the term enhancement is sort of one way of sort of separating out what gestures are being enhanced, which ones are not. And that enhancement will often occur in particular phonetic contexts, okay, and not in others, okay. Like the aspiration of stop consonants only occurs in pre-stressed position, basically. And so one has to be ready for that, okay. Now, the other kind of source of variability, as you well know, is that even in clear speech, the gestures are overlapped. Gestures of adjacent segments are overlapped, and that will also lead to additional variability in the signal, okay. In fact, as we'll see in this defining gesture that we've talked about earlier, we used that term, that may get obliterated altogether, and all you're left with is the enhancing gestures in some cases, okay. So it's just a few examples which are well known to you. You take a word like top tag, and then normally when you produce that, you certainly go through the gesture of making a labial closure and a alveolar opening, okay, in sequence. But quite often the labial closure, the alveolar closure is made before the labial release, right? So you don't get any sound at the time of the labial release. And so you get perhaps a longer interval here, and you get formant transitions corresponding to a P on this side and formant transitions corresponding to a T on this side, but no information about the release of the P or the closure for the T. Okay. So we have two landmarks here, and I should have said earlier that quite often if you have just an intervocalic consonant, you'll get a consonantal landmark and another one, both of which tell you information about that consonant. But of course there are cases where two adjacent landmarks correspond to different consonants, and one has to take that into account. If you speak more clearly, then you do get a P release and a T closure following on each other. And of course these two are exactly equivalent in terms of their feature representation. And in fact, a child of age 3 years old doesn't even notice the difference between these. Okay. They're the same utterance. But if you look at the details of the acoustics, they are different, and you just have to ignore that difference. So this is gestural overlap. And then, so you take a word like sudden, and as you again know, normally when you produce that, you don't necessarily do it this way, sudden, but in the underlying representation in terms of features, it certainly is a S-A, what is this sudden? Yes. And this is the D, and this is the schwa, and then this is the N. And so you get landmarks around the different consonants, and things are fairly straightforward. What's happening with the articulators is that somewhere during this vowel, you're opening up the soft palate, okay? And so you get some nasalization of the vowel, but the N closure might extend way back into the D, and so all you get is this thing, which is a syllabic nasal, okay? And so this syllabic nasal has a bit of a transition, but that's presumably what's happening as you're opening the soft palate. That's nothing to do with what's happening in the to the articulators, the other articulators. And so you get a landmark here and another one here, and then the end of it, and somehow the listener has to parse this as a schwa plus an n, okay? Okay. And so the features of the vowel show up because you have a peak in amplitude, and the features of the nasal show up because it has the right acoustic properties for a nasal murmur. Okay. So of these two successive segments, one needs to parse those, even though it looks like one acoustic segment, one has to parse it into two in order to access the lexicon, which does show the schwa. Okay. In fact, that's a point that, at least in the way we're doing things, we could have a second way of representing the word sudden, but we don't see any need to do that. Okay. There are going to be other cases where the landmark is not going to be easy to see, or maybe not, you wouldn't be able to see it at all. So if I have an utterance like saw a dog, which should have three vowels in it, saw, and somehow the comes in here, and then this is the third one. If you're looking at the representation of acoustic representation of a landmark as some peak in low frequency amplitude, you're probably going to miss this one. Okay. But if you say it more clearly, you might separate out these first two vowels, by maybe with a glottal stop or whatever, and you would see the individual syllables. Okay. So again, because of gestural overlap, you are missing something here, and somehow your analysis, by some means, has to take that into account. Okay. Let's see. And this is like the first example. We have a word like Batman, maybe a little different. So here's Batman, where you release the T, okay, and you get the M in here. And so every segment with its features is represented okay. But over here, when we say Batman, we may actually never have made a complete closure with the tongue blade, right? Batman. If you do it rapidly, you actually are not producing the underlying gesture that you, in a sense, should be doing for this T. However, and we've looked at this here, in this particular utterance, what you will often find is that the format transition, particularly of F2, corresponds to the transition, the fronting of the tongue body that I was talking about for a T, okay? In this case, it's only at the very end that you get this F2 falling, but up to that point, it's the transition that corresponds, you might say, to an enhancing gesture for this alveolar consonant, okay? And there's this overlap so that the M, closure for the M, actually you can see almost after the vowel has finished. So that this is possibly an example of a case where an enhancing gesture remains, but the basic underlying gesture that defines that utterance has disappeared, okay? In fact, there are a number of examples of that kind where the enhancing gesture sort of takes over, and the thing that actually originally defined, if you might say, defined this feature has been lost, in casual speech at least. So let's see, go on to So there are these two cases of variability in the signal that one has, are the main things that one has to deal with, and there are other sources of variability like prosody and so on, which I'm not discussing here. And so in kind of talking about these cases, kind of thinking of a bottom-up kind of analysis. What kind of cues are you seeing in the signal that will enable you to somehow extract what these underlying features are? But we know that this bottom-up analysis is going to, first of all, the bottom-up analysis, the way we often think of it, is it's kind of a local analysis. If you're looking for these cues in the signal, you're not taking into account, let's say, something that's happening a syllable or two later, right? But you're looking only locally. And there are going to be lots of cases where the context would have helped you if you had known what that context was at the time you looking for these cues. Okay. And the way it's been suggested, and it was suggested a long time ago, is that you do some kind of top-down analysis of the kind I showed at the beginning here. So this bottom-up analysis, you extract certain parameters, some cues, turn them into feature bundles, get some words, but given that you only have a limited context, some of these features you may be uncertain of. In fact, they will in fact always be extracted with certain probabilities, right? And so you'll end up with a cohort of proposed words here, or proposed word sequences. Now, if you have a cohort, let's say, take the simple case of 2 or 3 words, then what you need to do is take another look at the signal or take into account the context and either take a look at the signal or modify or look at the cues that you used. Okay, so for example, let's say you have an algorithm for identifying place of articulation for stop consonants. Okay. Now we know that identification of place of articulation for stops will depend upon looking at the burst, if there is one, looking at the formant transitions, and so on. And that in order to identify place of articulation, you may want to weight these cues, okay, with certain probabilities. Okay. Now, that weighting that you need to impose, we know, is actually going to depend a little bit on whether the next vowel is a front vowel or back vowel. There are going to be some differences in the way this consonant is produced, depending upon such a context. And if you had known the context of the vowel, let's say, then you might have used different weighting. Okay? If you didn't know the context of the vowel, you would have to use a weighting that was sort of independent of what the vowel was. But if you, by some means, can, in your cohort, have some idea of what the vowel was, then you could go back and re-examine these cues and maybe weight them a little differently now that you know something about the context. Okay. Or let's suppose part of getting the proposed word is to extract the formant frequencies, and you know that that is not too reliable, so that the proposed words might have several vowels that could have been present given your, let's say, noisy extraction of the formants. So given that you have a cohort here, you can go back and re-examine the input. But now what you're asking the input is a different question. You're not saying, track the format for me. You're asking, if I had this word, then I could internally synthesize roughly what a format track should look like if that had been the word. And I can ask of the signal, is this signal consistent with that internally generated format track? So that's a kind of thing that one might do. We haven't done that ourselves yet, but so that's another way in which this top-down analysis might help. There are a couple of things that were done at our lab that began to use this top-down processing. One of them had to do with this identifying the place of articulation for stop consonants. So here's a spectrogram of an utterance, I can't go up to Sweden. And that's an utterance we're using because it's has some of this overlap and some of this these problems with variability, right? So this K is coming through fairly well, but I can't go up is not. In fact, it's followed by a G, and it's possible that this G is influencing the N, and there's certainly no evidence, strong evidence of the T. In fact, in many utterances of this, you don't even see a nasal murmur. You just say, I can't go. Right? You don't even make a closure for the N or the T. I can't go. Right? This student, Atiwang, looked at, first of all, at the stop consonants in this utterance. And he had this algorithm for identifying place of articulation for stops. And he found, as I said before, that the weighting that you need to use for a number of parameters having to do with format transitions and spectrum of the burst and spectrum of the burst in relation to the vowel. He had maybe 10 or 12 parameters that were used to identify these consonants. And he found that the weighting of these parameters, if you trained this on all utterances, you get a certain weighting of the parameters. If you train it only on utterances, let's say, of these stops that had an adjacent front vowel, you get a slightly different weighting. And depending on whether the consonant was voiced or voiceless, you get a slightly different weighting. So these are the sort of probabilities that he would get for classifying the place of articulation for the stop consonant for the K in can't, the T in can't. In fact, there wasn't much of a T. And the G and so on. And he found, and these are probabilities in a sense that these consonants existed given the weighting, taking the context into account. And for this initial K, it was identified with high probability. It's a very clear one. For the T in can't, it was identified as a velar, okay? And so on. And then this up to, it just made it for the P, but there was no release for the P, so it was pretty marginal, okay? This is simply a demonstration that these probabilities would have been different if we had done the classification without knowing the context, okay? And knowing the context helped. So it's a sort of an example of this top-down. Let's see. Well, here's another case. We were sort of experimenting. There was a student did a little project on this. Let's suppose you take a hypothetical situation where all you want to do is identify consonant, vowel, consonant words. That's automatically, okay? And let's make it even simpler and say, let's see how well you would do if you knew what the consonant context was, and all you're trying to do is find the vowel. Okay, so maybe two situations. One, you're just looking at the vowel and trying to identify it. And second, you are making use of your knowledge of the context and try to identify the vowel. And so he had, I don't know, some 1,000 or so words out of a possible, maybe it's 6,000 possible words, but he had a subset. Okay. And so if he was just looking at the middle of the vowel, trying to identify the vowel, I think there were 11 vowels, the percent correct identifying the vowel, and this is with machine format tracking, although it was trained on format tracks that were maybe hand-corrected. Okay. And the score was a little over 50%. And then he took into account knowledge of the consonant in a way using kind of a top-down analysis. And he did that in two ways. One is knowing the consonant, or knowing both consonants, you have some idea of how the consonants, you know that consonants influence the duration of the vowel, right? If a voiced consonant makes the vowel longer, a voiceless makes it shorter. He took that into account and normalized for that. And he normalized for a number of other things. I won't go into detail. Normalized the first format across the speakers. There were two male, two female speakers, and normalized the second format. There was a lot of detail here. But that was one way to kind of taking into account the context and compensating for it. And the other was when he tried to identify the vowel and was given the consonant, sometimes it would come up with a word that was not in the lexicon, so you'd have to pick the next best word, okay, was not in the lexicon. And so just an example then that he was able to improve the vowel identification score by quite a bit by taking these factors into account. It was simply an exercise of using a context and the lexicon for adjusting your estimate of the bottom-up processing. And then one other example. So in that word can't, I can't go up to Sweden. Let's suppose that a first pass with bottom-up processing without taking into account the context came up with maybe a set of cohorts like that. Okay. One would have to sort of understand the details of how you can come up with both of these, but it may be that on a first pass you don't necessarily look for nasality over the whole vowel. And so given this set of cohorts, let's say in trying to, once you've got, say, these two cohorts, then what that would trigger you to do would be to look for nasality in the vowel, okay? And if you look for nasality near the beginning of the vowel, you would see a spectrum that looks like this. If you look farther on in the vowel, you will see a spectrum that looks like this, which looks kind of a subtle difference, but we do know that the nasalization will usually give you an enhancement at low, in around 1 kilohertz, actually a pole zero pair here, and will often reduce the amplitude of the first format. And by looking at this particular measure for nasalization, then you can resolve this difference and say it has to be this one. Okay. And then, of course, looking in more detail at the vowel, you could resolve these two as well. Okay. So those are examples of this, you might call it top-down processing. So let's see. Here's summary. How am I doing? So these are kind of things I've been trying to say. So, okay, we represent words in memory as these bundles of distinctive features, and basically we're suggesting that each word has one representation. Now there are going to be cases where you may need more than one. Like if there might be a word like wanna for want to, which would be hard to even though you might be able to figure out how that comes from want to, it might be easier to store words for that. Distinctive features are based on these kind of quantal articulatory acoustic relations, which specify defining articulations, defining acoustic attributes. And so these distinctive features, the view here is that they're universal. They're dependent upon how we produce sounds and perceive them. And so the acoustic correlates of a feature are enhanced by certain additional gestures, and so that a given feature may have multiple acoustic cues, as you well know. And that additional variability comes from this gestural overlap, and that we had an example, and there are other examples where these defining attributes are actually maybe obliterated or masked by the enhancing ones. Right? In fact, it's always a question when, if you're looking at a given language and what the distinctions are in the language, which are the defining gestures and which are the enhancing ones. But that's another whole question. So the articulator-free features give rise to acoustic landmarks, or discontinuities, and peaks or valleys for vowels and glides. And the acoustic cues for the articulator-bound features usually reside, once you've got these landmarks, in the vicinity of the landmarks. And then finally, contextual information is often manifested in regions that are more remote from the landmarks. And so, for example, if you know that a word is a utterance final word, it's going to be produced, let's say its final consonant is going to be produced in a different way as you reduce the subglottal pressure and so on. And that is another kind of contextual information that you might want to take into account in sort of evaluating identifying the words. So top-down processing is of some kind is certainly needed to select a candidate from a cohort that has resulted from the local bottom-up analysis. So this has been sometimes called analysis by synthesis. Okay. So that's it. Thank you. Mm-hmm. Mm-hmm. Maybe some questions. Yeah.
I was a little confused about the distinctive feature versus the enhancement. When you say distinctive features are universal, what universe are you talking about? I mean, how?
I would say across the languages of the world.
Okay, so this is true for all the languages, and enhancements actually differentiate?
They would be different for different languages, right? They may well depend upon the enhancements that you might use, depend upon the inventory of features, depending on the contrast that you have in the language. And so if you want to enhance a given contrast, you might use a certain method in one language, but not in another. So, for example, Spanish, let's say, doesn't distinguish tense from lax vowels. Okay. But Spanish actually makes its vowels a little bit more tense. They sort of make the vowel E, for example, a little more extreme than our vowel I in English. Right? So they might, or they might do it in a different way. That's all. Yeah. So is there any? And of course, one of the problems is to know what's enhancing and what isn't.
So the distinctive feature literally is then connected to the physics of the human body.
Right, right, and the articulate and the auditory system as well, of course. And I didn't talk much about that, but I'm assuming that if the acoustics looks distinctive, that the perception looks distinctive. But there are some features where you're going to depend on perceptual properties as well. Okay, but it's some coming together, let's say over evolution, I suppose you might say, of these kinds of quantal regions, right? In languages of the world. Some languages have clicks and others do it differently and so on. Yes?
Could you talk a little bit about some of the evidence you mentioned that this is in fact how humans recognize?
There are a lot of things I guess one could say, but as you may be aware of the early work of Miller and Nicely about if you let's say do an experiment where you use just consonant vowel syllables and with, let's say, always with the same vowel but have a whole bunch of different consonants, and you present these to listeners in various amounts of noise or various kinds of filtering and look at the kinds of errors they make. The errors seem to line up according to the features quite often. Okay, so that's one piece of indirect evidence. I guess another kind of evidence, which I guess for me is a little bit anecdotal, in that a lot of and these are just not experiments at all, but some of these effects, like top tag as opposed to top tag, or I'm going to, or I'm gonna, children don't even know the difference. They will say either one and without any trouble. Okay, so there's some evidence that they have some way of representing this that is kind of ignoring these overlaps in particular. Okay. What else? Well, of course, the evidence for the features comes originally a lot from the linguists, right? That is, we have somehow knowledge in our heads of these features. An example, for example, is we know how to make a plural in English. We know whether to add a z or a s or us, right? And if the example that I hear the linguists give often is if I take a foreign word like Bach, right, and I want to add a plural to that, what I do is add an S, right? And I think everybody would add an S, and that's because you know what the features are of the last segment. And there's a rule which says if it's voiceless, you make a voiceless S. So that we have kind of some knowledge in our head, or a new word comes along and we know how to make the plural, or we know how to make the past tense or whatever, because we know about some rules that involve these features. There might be other things, and in fact, we probably need to look a lot more at how humans do it. Okay, but those are some examples.
I have a question. So you said that these distinctive features have some gestures that sort of are used to realize them in the acoustics, and then there are the enhancing gestures.
Yes.
So does it then follow that if there is a feature which has a enhancing gesture that's permissible in a context, then in fact the gesture of the feature itself becomes optional and could be reduced, deleted? You're deleting the T when you can.
I wouldn't necessarily say that that's true, always true.
Okay. What
But,
I was hoping for is that one could then take all these enhancing gestures, compile them into a set of rules, and then take a dictionary and then produce alternate pronunciations sort of automatically saying
Yes.
these are all the ways in which these words
Yes.
should be pronounced.
Yes.
And I was thinking of somehow perhaps finding some use for it in mathematics.
Right. Right. Exactly what the form of those rules would take is unclear. I mean, sometimes those enhancing gestures look like features. They look like the representation, or it looks like a different segment which has different features. So, for example, in English we have, let's say, pa, which is aspirated, right? And at least I'm arguing that that is an enhancing gesture. But it's pretty much the same huh as they have in some other languages where that is a distinctive feature. But yet there are other, it seems to me, there are other enhancing gestures which are more graded. And so it's a little harder to assign rules when it's not a plus or minus. So like, well, rounding in sh, for example, it's probably graded, but that's maybe not a good example. Lengthening of a vowel before a voiced consonant is kind of graded, I think, if it's in final position. But nevertheless, yeah, it would be possible, I suppose, to assemble an inventory of alternate pronunciations. But I just worry about expressing those relations in terms of, let's say, what I think are usually called phones. They might, there'd have to be in some of them might be, but some other language.
Right,
I'm
exactly.
thinking.
So these would end up creating segments which don't fall in the standard list. For the
Right,
language, and
right.
therefore-
But that's a way that people often do, right? I mean, so I'm sure that there are often phones which are syllabic nasals, for example, right? You know, yeah, it's a way of doing that.
And the other question I had was this evidence about whether people do this. So when it comes to these enhancing gestures, do we see more of them, for example, in child-directed speech, maybe, where we kind of teach children
Yeah.
what these sounds are?
Good question, good question. And so there's a student in our lab who's looking at kids, not so much for this purpose, but I'm looking at it for, to see whether there's any, whether enhancing gestures sort of come later. I mean, you might think that the defining ones are first and so on, but I'm not so sure that happens. The kid picks up on everything. And in fact, it may happen the other way around. It seems to me I've read about this, that the kid is able to deal with these things, and it might be only later that they start of figuring out what are the actual contrasts, what are the really the fundamental distinctive features. But that's certainly a great question to look for, to answer. Yeah. Mm-hmm.
Another question? Let's thank our speaker again.
Thank you. Mm-hmm.